Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Okay, good. So, all right, I think all of you can hear me. So let's start. So we will continue our class on this topic, which is a discrete time Fourier transform, and this is actually part 4. Okay, so we have started the chapter before mid semester, and then so this will be the hopefully will be the last class. So if you don't have enough time to complete it, then we will continue next week. Okay, so before that, let's see something. So this is actually, okay, wait. All right, so this is our plan. So we are here now at week 8. So this is our title, DTFT, Discrete Time Fourier Transform. And for the assignment phase 1, so we are actually at the second part. So second part is on home group forum. So which is, what is the main task? The main task is to combine all your individual notes. Because everybody should have your individual notes. Now you need to combine those notes into one page. So you need to think that if your notes is a bit complicated, your individual notes, so you need to think on how to simplify it, because now 5 different individual notes needs to be on one page. Okay, so what will be the end product? The end product is that notes. That notes needs to be, you need to put it on Jamboard. Okay, so we have a Jamboard for week 3, which is next week. So you need to put it on the Jamboard. So before the end of the week. All right. So please continue doing the forum. And first week forum, whoever still maybe doesn't get a full a 3 rated post, you can still post to the forum, right? And you can still submit your individual notes. Okay, so but you need we need to progress into the second week. So you need to if you still didn't get a 3 rated post, so it means that you need to do a 2 forum. You need to post to 2 forums. All right. Okay, so this is week 8, and let's see. So we are in this discrete time Fourier transform. So we have seen what are the 5 different types of frequency, and then we have seen the formula for DTFT. So this is the formula for DTFT. And lastly, from previous, so we have seen one example. So which is this one. Okay. Which is at the end of this example. So we have seen that we are plotting the magnitude. Sorry, this is the real part of our H omega, the frequency response. This is the imaginary part. And this is the magnitude. And this is the phase spectrum. Magnitude spectrum, phase spectrum. Okay, and we are actually plotting this response, this frequency response, using a shifted plot. Okay, because we have 3 types of plots, and this is actually using a shifted plot. Okay, so before that, I think it's good if we have some recap on what we have learned before we go to the next example, so that we can refresh everything. Okay, so this is our title, Fourier transform. Generally, it is a Fourier transform, but why we have DTFT? Because actually we are looking into a discrete time and system, a discrete time signal and system. Okay, because actually it is whether it is a continuous discrete time. So actually what we do is we are transforming our time domain signal into a frequency domain. So if we have a continuous time, this is a continuous time, the notation, you can see that. So this is x, which is in time domain, small x, and then we are using t. T means a continuous time. So if you do a Fourier transform, this is actually from previous courses. One of it is signal and system. So you will get a plot, okay? So this is a response. We call it a frequency response. So which is if in a frequency domain, so we use a capital letter. Instead of a small letter, time domain, capital, we use a capital letter in a frequency domain. And what we get is from time, the x-axis of the plot in time domain. So we are now using the frequency domain, which is in hertz. So why it is in hertz? Because this is in continuous time. Okay, and the unit is hertz, and what is the range? The range is from 0 up to your maximum frequency. So whatever the signal you have, so it will plot everything, okay, from 0 up to a frequency of the frequency, maximum of that frequency. And we have seen that instead of frequency in hertz, we also has a frequency in angular. So this is what we call an angular frequency. And we use capital omega to denote the angular frequency. So why do we have this 2 pi f? So why suddenly, originally you have a f in hertz, that capital F, and then suddenly you multiply by 2 pi. So because this is what Fourier have done. So what Fourier do is actually it's decompose any signal. Any signal can be decomposed into sinusoidal signal, either sine or cosine, and within that equation, the sinusoidal signal, so there is distance 2 pi f, so that the frequency can be denoted as an angular representation. Okay, because to represent repetition. Okay, to represent repetition. So that's why we have 2 pi f. So we call it angular frequency. Right. So then this is not our focus this semester. Our focus is this one. So which is the discrete time signal and system. Okay, so if you have xt, so how do you get xn? So you do sampling. So, and you do sampling with fs. So fs is actually number of sample in 1 second, frequency sampling. If your frequency sampling is 100 hertz, means that you will have sample 100 sample in 1 second. All right, and this is the relationship between t and n. So where t is actually equals to n over fs. So this is where when you do a Fourier transform, when you want to convert or transform this time domain signal into a frequency domain. So we do discrete time Fourier transform. That's how we differentiate. We just call it Fourier transform if it is for continuous time. We call it discrete time Fourier transform if we are actually doing it on a discrete time signal. Okay, so that's how we differentiate. So this is actually our focus this semester. So not this one. So this is from previous. And even the F is we're not going to use a capital F. We're going to use a small f. So what is a small f? So this is actually the relationship. So that small f is actually equals to f, that capital F in hertz, divided by our frequency sampling. So it is a ratio. It is a ratio. It is a ratio between the physical frequency divided by our frequency sampling frequency. All right, and this is where when we do this, so actually the range becomes up from 0 to 1. So this is the range that we get. So that's why, because the range is from 0 to 1, so we also call it normalized frequency. So either we call this, because this is divide, so we call it ratio. So we can call it as a frequency ratio. And because the range is from 0 up to 1, so we can also call it normalized frequency. Okay, either one. And same thing, this small f, because that capital F can be multiplied by 2f, because we are still using the same decomposition of signal using sinusoidal sine and cosine signal. So we can also multiply it by 2 pi. We have this term. And we call it angular frequency. But instead of using capital omega, so we are using small omega. Okay, now we have 4 different type of frequency. This is a capital F, small f, capital omega, small omega. Okay, these two are actually for continuous time, and these two are actually for discrete time. And we have another one, which is if we see here, so what we do here is we are doing sampling on time. Then we get discrete time. Okay, but we didn't do anything to the frequency. So we didn't sample the frequency. So to make everything discrete, so we need to sample the frequency also. This is later, so there's there's a variable n here. So, but we will cover this later. So to do the sampling to the frequency, we need n. To do a sampling to the time, we need fs. The same thing, we do sampling. So then our frequency becomes a discrete frequency. We denote it as a k. Okay, we're going to use that k. And we have what we call if you have a discrete time signal, do a Fourier transform. We call it discrete Fourier transform. Okay, Continuous time, Fourier transform. Discrete time Fourier transform. But frequency still continuous. To have everything in discrete, so actually we are doing discrete Fourier transform. And this is the relationship. So we have this relationship between this small f and then f and fs. So we have this k. So you have all those relationship between f, the small omega, a capital omega, whenever you have this k, right? You doesn't have to memorize this. It doesn't have to memorize this because in test and exam, this formula will be given. Okay, you just need to know how to use it. So what does it mean? Actually, we can convert between these 5 frequency, 1, 2, 3, 4, 5. We can convert it between each other, right? Because actually, whatever you have in your PC, when you do MATLAB or if you do Python or whatever the programming language that you use on your PC or on your digital system, actually what you do is a discrete Fourier transform, because this is where you have everything discrete, okay, everything digital. That's why discrete time Fourier transform is actually just a theoretical knowledge. So it's not an implementation. The implementation is this one. So, but when we do analysis in MATLAB, maybe Python, or any software, okay, or any software. So what we do is actually we are converting this k into these 4 other frequency. So if you want to analyze it on hertz, you need to convert this k into hertz. Okay, because originally you have this. On your PC, you have this one. So what is a capital F according to K? So it is a FSK over N. So you need to do that conversion. Then you will have your x-axis plotted on hertz, a frequency in hertz. Okay, but of course, many software, they already did that automatically. When you do the plotting, when you do the function, it's already plot the x-axis as hertz. Okay, some of the software function already do that automatically. So, but actually it converts the k into that f, capital F. And what we have seen is also these 3 things when we do plotting. So because we need to really understand this, the original is actually what we call a whole plot. Okay, and then we have also shifted plots. The whole plot, it start with 0. So it starts with 0. And for omega, small omega, the range is actually from 0 up to 2 pi. Okay, actually the maximum frequency is pi. So this part is actually the conjugate pair of the other side, right? Shifted, we start from negative. So if it is for omega, small omega, if this is a 0 up to 2 pi, so we start with negative pi up to pi. The same thing. So this is actually one part of our plot. This is just the conjugate. Okay. So this is where actually many software, many functions, they plot only this one. So we call it half plot. Okay, we doesn't need to plot everything, because when we want to analyze, so we just need a complete information is actually, you can have it on half plot. Okay, and it becomes less confusing because we are looking only half of it, because if not, you will have a mirror plotting. The whole information plus the mirror plotting. So maybe you will get confused on that. Okay, so this is, normally we use this half plot. Okay, because everything is there. And we need to know the range for this omega, small omega. Actually, the range is from 0 up to pi. If the small f, the range is actually from 0 up to 0.5. And I think last time from our previous class, so I made a mistake. So I put this as a 1. Okay, so please correct that one. So this is actually from 0 up to 0.5, not 1. Right? And if it is in hertz, so actually it is from 0 up to fs over 2. Our frequency sampling divided by 2. So that will be the maximum frequency because of the Nyquist theorem. Because of the Nyquist theorem, actually our maximum frequency is Fs over 2. Okay, if you still remember Nyquist, what is a Nyquist? We need to pick frequency sampling is 1. Frequency sampling should be greater than or equals to 2 of our maximum frequency. Then what is the maximum frequency? So that 2 bring down, so you get Fs over 2. So that's what we have here. Okay. All right. Any question? Because this is just we are doing some recap, so that's everyone knows what's happening. And so far, so what we have is we need to be very we need to understand, and we need to be able to identify these 4 characters. So what are those characters? Impulse response. Okay, one of it is impulse response. Another one is difference equation. So you need to know exactly what is impulse response. Impulse response is Hn. Okay, in time domain. What is the difference equation? Difference equation is a relationship between input and output. Also in time domain. Yes, this is actually Among Us, but because I did this notes last year, that time Among Us is quite popular, so I made it. So okay. What's next? Impulse response, difference equation, and then this is another one, system function. This is Hn. This one is Hz in Z domain. So 2 of these in time domain. This one is in Z domain. Okay. So the other one is the one that we just learned starting from week 7, which is a frequency response. Okay. So we need to know what is the relationship between these 4. All right. Okay, let's look at it. Impulse response and difference equation for FIR. So it is just very straightforward. So we have seen this. Hn is actually equals to coefficient B. All right. So that's the relationship. But for IIR, it's not that straightforward. So we need to do something. What is the relationship between this one? You need to do a Z transform from impulse response to system function. And look carefully, the title here, this is a frequency response of a system. Okay, be careful. We are referring to system, not signal. Okay, because if it is a signal, we don't have system function, we don't have impulse response. It doesn't have difference equation, because difference equation is for system. Impulse response is representing system. System function is also actually representing system, but in Z domain. So if it is a signal, can we do Z transform to a signal? Yes, we can do it, but we doesn't call it system function. Okay, so that's the difference, because doing a Z transform is just actually we are doing multiply this Z to the power of minus n to a vector. Impulse response is a vector. Even signal is also a vector. Okay, so what is the difference? If we do to a signal, we don't call it as a system function because it's not a system. Okay, what else? Next, this is difference equation to system function. So we have seen this also in week 6 last time. Okay, this is the relationships. So what is actually Hz? Hz is actually just your Yz, your output in frequency in a Z domain divided by your input in Z domain. Okay, so that's the relationship. And then this is new. This is new. So we have seen this on last Thursday. So how do we have our frequency response? So this is our focus today, actually, the frequency response. So we will do a DTFT. So this is actually a DTFT. So our Hn multiplied by e to the power of j minus j omega n. So that's what we call a discrete time Fourier transform. Right? So we do that. And so we have seen this relationship also. So what is actually frequency response in terms of a system function? Because Fourier transform is actually just a subset of Z domain. Okay. So what we do is actually we are setting the radius. The radius equals to 1. Okay, so that's why it becomes an EJ omega. So instead of the full definition of Z is actually REJ omega. So because the R is equals to 1, then now we have this one. Okay, so let's see a simple example here. Let's say we have a Hn equals to 1 to 1. Okay, this is stable, this is causal. Stable and causal, and this is FIR. Because we have only 3 samples. 3 samples means this is finite. Finite, it is a FIR. Okay, so then what is the difference equation? Because Hn is actually equals to B, the coefficient B. So what we have is just we going to transfer this straightforward. So what we get is a Yn equals to Xn, because this one is multiplied by 1, and then this is multiplied by 2. This is number 2. Okay, and then this is a 1, so multiplied by 1 here. So this is the difference equation, straightforward, because this is FIR. Very simple. And coefficient B is that one, 1, 2, and 1. And what is the coefficient A? Coefficient A is 1, because we only have one output sequence. And what is the multiplier? Multiplier is 1, so that's why it is 1. And this is the HZ, also very straightforward, because this is how do you get this? You can refer to table, okay? Z transform table. So because we have 1 to 1, so you have this 1, 2, to the power of minus 1, because delay by 1, this is delay by 2, Z to the power of minus 2. Okay, straightforward. And what is the frequency response? So we have seen this in our last class on Tuesday, because Z is actually equals to EJ omega, so you just replace that Z. So it becomes 1 plus 2 EJ minus J omega plus minus J2 omega. Okay, and from last class, so we already know that H omega is a complex value. So we can separate this. So we can separate this into real and imaginary. Okay, so from here. So but if you work out on this one, so actually the real part is actually equals to 1 plus 2 cos omega plus cos 2 omega. So how to do that? You need to expand this using Euler's equation. E minus j omega is actually equals to cos omega minus j sine omega. Okay, that one will not be given in that formula is not given in test and exam. You need to memorize that. The Euler's formula, you need to memorize that. Okay, what is the E minus j omega? Equals to cos omega minus j sine omega. So what is the E minus j2 omega? It is a cos 2 omega minus j sine 2 omega. All right, so this is the imaginary part. This is the real part. But if you still remember, this real and imaginary part doesn't give us much information. So we need to convert it into magnitude and phase. Right? Magnitude is just whatever you have in your real part, put a square to it, and then whatever you have in your imaginary part, put a square to it, and then plus square root. Okay, you will get your magnitude. Phase is just a tangent inverse of the imaginary divided by real part. And we also have this kind of plot other than magnitude and phase. So we also have a H omega squared, a magnitude squared, or we call it energy. Okay, other name for this one is energy. And we also normally many times we're going to plot it in dB. Okay, so why we plot it in dB? Because it's for visualization. Most of it is for visualization. Because some plots, there will be some very small number. So that's why we need to rescale. We need to rescale our y-axis so that we can see everything. Okay, not for calculation, just for visualization. Right? Okay, so that's all for the recap. So hopefully you guys can remember everything after this. At least remember the names. Okay, so what is the function? And again, these notes is available in e-learning, so you can always refer to it. All right. Any question before we move to our next example? Purple is Sus.
Okay, doctor.
Okay, all right. I forgot the name, all those names. All right, so, okay, this is from last time. So we're going to look at the next example. So which is, last time, what we do is, if we look back at this example, example 1, so this is actually FIR, okay? And what's given is impulse response. Okay, so this is FIR, and this is actually our impulse response. Okay, so we're going to look at on a different angle of example. So what we have now is difference equation. Okay, we need to find magnitude. So what is this? This is magnitude, and this is phase. So this is magnitude response. This is phase response. Okay. Sometimes we call it magnitude spectrum or phase spectrum. The same thing, because the spectrum is actually referring to a frequency plot. If you have a frequency plot where the frequency is at x-axis, so we call it spectrum. And this is difference equation. In example 1, so what we have first is impulse response. Okay, so we're going to look at this one. Right, so that's why we have this recap. So that's actually, you know that we have impulse response. We also have difference equation. So questions and problem can start from any of these four. So maybe you are given system function, and then you need to solve something. Maybe you are given frequency response, and you need to solve something. Example 1, you are given impulse response, and then you need to find frequency response. Now, example 2, you are given difference equation. We need to find the frequency response. Okay, so which part of the frequency response? The magnitude and phase. We need to find that. Okay, so what is the difference equation? So we have yn equals to xn minus 0.5 yn minus 2. So what is this? Is this a FIR or IIR? Anyone? FIR or IIR? So when we have yn equals to xn minus 0.5 yn minus 2.
FIR.
FIR? IIR? Okay, IIR. So this is infinite impulse response. Because actually, by just looking at this, we can guess that this is infinite impulse response because we have this one. Okay, for FIR, we doesn't have, normally we doesn't have this one. Okay, what is this? This is output sequence. Output sequence other than yn. So yn is always there, but now we have additional output sequence. So which is yn minus 2, a delayed output by 2 samples. Okay, by looking at that, so then we know that this is actually IIR, and we need to know, like this slide. So normally what should you do next is to identify what will be the coefficient. In this one, A is equals to 1, and then B is equals to 1 to 1. So this is 1, 2, and 1. And in this case, our A will equals to 1. And we have a delay by 1? No, we doesn't have delay by 1. So it will be 0. And this is actually delay by 2. If you bring this to the left side of the equation, then this one becomes positive. Okay, that's your A. And your B is, because we have only one output sequence, so that's your B. Okay, so we always have to filter coefficient. So these are the coefficient. And because of that, so okay, so this is where we bring this one here. And then if we go back to this one, So what we do next is actually we are going to convert it into system function, which is hz. Okay, so what we do in that example, what we do is actually from here, we'll go to hz, and then we go to frequency response, h omega. So this is the root. Okay, let's go back. So from there, so this is why we are actually finding the system function, the hz. So what is the hz? So we need to convert this into yz. This is xz, and then we know that using the properties of a z transform. So this is actually a yz multiplied by a z to the power of -2, because this is n minus 2. So this is what we get, and then do some manipulation, a rearrangement of the equation. So you get hz equals to 1 divided by 1 plus 0.5 z to the power of -2. So it doesn't stop there, because we need to find h omega, right? And then what is the relationship between z and omega? So it is a z equals to ej omega. Then we need to change this one, change this z into ej omega. Then we get our frequency response. So this is what is this? So this is what we call a frequency response. Look carefully. So I'm writing it as a frequency response. And what is this? Magnitude response. This is a phase response. The original response, which is a frequency response, is actually in terms of real and imaginary. So this is actually in terms of real and imaginary form. So this is where we call it frequency response. After you put a modulus to it, so it becomes magnitude response. If you do tangent inverse to the imaginary and real part, we get phase response. Okay, the original is a frequency response, so we call it frequency response. Okay, so this is what we have now. Next, we will find these two, magnitude and phase. So in order to do that, so next we need to find the real and imaginary part, because this is actually a combination of both. So what is the real part? What is the imaginary part? So not clear. Okay, so we need to separate that. To eliminate the j at the denominator, because we have this j. If the j is actually on the numerator, that one will be easy. Okay, that one will be easy. But because this is at the denominator, so we need to multiply with conjugate values, the conjugate pair. So whatever you have here, multiply with its conjugate. So what is a conjugate? Conjugate is if you have a complex number, the real number will be the same, but the imaginary number, you change the signs. Change the sign of the imaginary. So what is the imaginary? This one, j. Because this is negative, and now change it into positive. If this is positive, change this one into negative. Okay, so just that, because we have 1 plus 0.5 ej to omega at the denominator, so you need to have it on the numerator also. So that's why then this one becomes 1. Then the whole thing is actually equal to the original frequency response. Okay, so then do that, the numerator, so we'll have that 1 plus 0.5 ej to omega, and then the other one is multiply 1 multiplied by 1, and then 1 multiplied by 0.5 ej to omega. This is a 0.5 e minus j to omega multiplied by 1. So you will get this thing. Okay, so what we see here is the denominator becomes all real values only. That's what we want. That's actually the objective of multiplying with conjugate. So after that, so this is the last one, and then rearrange everything, so we get this thing. So 1 over 1.25 plus cos 2 omega. So this is a real value. This is a real value. And this one, ej to omega. So what is the Euler equation? So ej to omega becomes cos 2 omega, and this is becomes plus, because this is plus, plus j sine 2 omega. And of course, we have that 0.5. So 0.5 here, 0.5 here. So actually, this is the real part. this is the imaginary part. Okay, we have separate. So we have separate the real and imaginary. Then we can do the magnitude and phase. Because the magnitude and phase is we need a real squared plus imaginary squared square root. Phase, the tangent inverse of the imaginary divided by real. And this one, it can be just some multiplier only. Okay. Okay, to estimate the plot, because we want to plot. So we want to plot. So let's see. So what we have. So because we have three types of plots. One is the whole plot. The other one is a shifted plot. And last one is a half plot. Okay, let's do the whole plot. If you do that, and this is omega, because we are actually dealing with omega. Okay, we're going to use this frequency. In DTFT, most of the time, we're going to use omega frequency, which is in radian, small omega, not capital omega, right? Okay, so what is the range of omega? The range of omega is, if we look back here, the whole plot. So this is the whole plot. Omega, so we have from 0 up to 2 pi. So this is the one that you need to plot. Okay, but of course we cannot do every value. So that's why we are estimating it on several points. So here we will try to do on 0, pi over 4, pi over 2, 3 pi over 4, and pi. So what is pi? Pi is here. If you have your 2 pi is there. Okay, and we will try to do, because this is some estimation, this is a pi over 2. And then this is pi over 4. This is a 0. This is a 3 pi over 4. Do we need to compute this part? We doesn't need to compute this part, because this is a conjugate pair. This is a conjugate pair. So what is a conjugate pair? The real part is the same. The imaginary part change the sign. So it doesn't need to compute it. Okay. So if you have something here, this one is actually equals. Those two are conjugate. We cannot say equals. It is a conjugate pair. So we need to, we doesn't have to compute it. Okay, so now this is our target, because we want to estimate. When we do estimation, we cannot compute everything. Okay, cannot compute everything. Even if you do the MATLAB, so it will do, let's say, how many points. So you need to pick. Maybe you pick 1,000 point. Maybe you pick 100 point. Okay, those who have done the frequency domain, I think you have seen the function. So you need to pick a number of points. If it doesn't pick number of points, so that is actually a default value. So that's a default value. Okay, so let's see now. The easiest one is actually to find H0. This one, H0. This is H omega. This point. So we're going to find H0. Okay. So what will be the y-axis? So this is what we are trying to find out, right? And of course, actually we are doing two things, not H omega. One is a magnitude, and we should have another plot. 0, let's say this is pi, this is 2 pi, this is pi over 2, pi over 4, this is 3 pi over 4, this is omega, this is phase. So we should get two values. On 0, so what will be the magnitude? And what will be the phase? Okay, let's do that. For omega equals to 0, so because we have this equation, so we're going to plug in 0 value. Okay. when this is 0, so this one becomes 0, this becomes 0, this one becomes 0. So what we are going to try to solve is actually 1 over 1.25 plus cos 0 multiply to 1 plus 0.5 cos 0. This is a sine 0. So what we'll have is, so this is the one after we replace omega equals to 0. So those are 0, then 0, cos 0 is 1. Cos 0 is 1, sine 0 is 0. That's quite basic. So sine 0 is 0, then this one becomes a 0, this one becomes a 0.5, and then plus 1. So becomes a 6.5. And then this is a 1.25 plus 1. So what you get is a 1.5 divided by 2.25, 0.67. Okay, H0. So what is this? H0 is actually equals to 0.67 plus J0. No imaginary, just real part. Okay, so that's it. So from here, so what we'll get is just 0.67 square root. So it becomes a 0.67. Okay, this one. And what will be the phase? The phase is a tangent inverse of a 0 divided by 0.67. Because imaginary is 0. So this is the imaginary. What is the real value? 0.67. So this is a 0.67. So do that, tangent inverse of 0 becomes a 0. So what will be the value here? This is a 0.67. And this is a 0. Okay? Phase, a magnitude. So this one is the phase of H0. So, okay, so let's go next. We will try to find when omega equals to pi over 4. So for omega equals to pi over 4, so again, replace that omega into pi over 4. Then we're going to solve this, the same equation. So this is actually the real part. This is the imaginary part. So plug in as a pi over 4. Because the equation is, let's go back to the original equation. So this is a 2 omega. Okay. 2 omega, when we change it into a 2 pi over 4, so this is where we get pi over 2. This is where you will see pi over 2 here. Pi over 2, pi over 2, pi over 2. Okay, do that, solve it. So you will get frequency response at pi over 4 is 0.8 plus J 0.4. The real value is 0.8. The imaginary value is a 0.4. Okay. Then we do that magnitude. Magnitude is just a square of this plus a square of this and then square root. So we get 0.89. And what is the phase? Phase is a tangent inverse of this one. This one divided by this one. So you will get 0.1476 pi or 0.4636. And this is in terms of pi. Okay. So of course you need to divide by pi to get this one. 0.15, so almost 0.15 pi. Ready. Okay, one is a 0.89. So what is this? So this is a 0.89. And the other one is a 0.15 pi. Let's say this is a 0.15 pi. Okay, what is this? So this is a phase at pi over 4. So this one is a magnitude at omega equals to pi over 4. Right? Magnitude and phase. So, okay, so that's the idea of how to do it. So when you do a pi over 2, you will get these values. H pi over 2 you'll get 2. After solving this, you will get only real value, no imaginary value. So the phase is again 0 here. And then this is for 3 pi over 4. You will get a 0.8 minus j 0.4. And you will get 0.89 for the magnitude. And this is minus 0.15 almost. Okay. If you want to simplify that a bit. 0.15 pi, but this is a negative. The first one, we get 0.15 pi positive. So let's say this is a 0.89. This one is a 2. So actually at here, you should get 2. Okay, 0.67, 0.89, this is 2. And then the next, 3 pi over 4, 0.89. Okay, and then what is the value for this one? So a 0, 0, and minus a 0.15. This is a 0 again, and then here, minus 0.15 pi. Okay, that's how we estimate that. And of course, you can continue to pi. For pi, what you will get is 0.67. So magnitude is a 0.67, and the phase is 0. So let's do that, 0.67. Okay, so this is what we have here. So if you want to plot it somewhere here, so you just copy as a conjugate. For magnitude, everything will be the same. So this is going to be 0.89, and this is going to be 2. This is 0.89 again, and this is 0.67. Okay. So because this part is just a conjugate. The conjugate pair. So this is whole plot. So this is a whole plot. Magnitude, you just copy. But for phase, so this is where now we have this one. So this one, it will give you a different sign, opposite sign. This one and this one is actually conjugate pair. So because it is a conjugate pair on phase, the sign will be changed. Okay, the sign will change. So then this is will be 0, this one will be 0, then this is going to be negative 0.155. Okay, so that's actually the difference between magnitude and a phase. Magnitude, everything is like a mirror, totally a mirror. So this is like an opposite mirror. It changed the sign because of that conjugate. If you do that tangent inverse, it will change sign on phase. So this is okay. So that's how you do that. Of course, if we do manually, so this is what we'll get, only a few value. We can compute only for a few values. So this is where to have a complete analysis, so we should use some simulation software like MATLAB. Okay, for example, it is MATLAB. There's other simulation software that we can use. So, but MATLAB is one of the easy software or tools that we can use. So if we use MATLAB, so I think this is maybe around 1,000 samples. What we did calculate is just like 4 or 5 samples only. Okay, maybe this is all for 1,000 samples, 1,000 points. So this is where we can plot it very smooth. This is a 0.5 pi over 2. So what is this? So this is equivalent to pi over 2. So it is equals to 2. So this is the one that we have just now. Okay. So this is the this is a 1, okay, up to here. And this is actually half plot, because we just plot it up to pi. If you want to have a full plot, so you should have until 2 pi over here. Another, okay, so this is a full plot. So you will have another part which is the conjugate of this plot. And this is the same thing. So if you want to plot it as a full plot, so you should have a 2 pi here, and then everything should be, let's do something here. Something like that. So whatever the sign here, change the sign. Positive, negative. Okay, so that's how you plot it. But for analysis, so actually it is enough to do a half plot, so that we will know what is actually this filter will do. So if we look at this shape, so actually this is what we call a band pass. Okay, this is a band pass filter. So we have a very low value at lower frequency here, a very low frequency magnitude on a higher frequency, and a very high magnitude at 0.5 pi. So it is a band pass filter, which is actually focusing at 0.5 pi frequency. Okay, so it is a passing frequency, maybe somewhere, most of it somewhere here. Okay, because the rest is maybe you will have less than, it will reduce it up to maybe less than 0.5, something like that. So, right, so this shape, so it is a band pass. Okay, any questions? So we finish on a second example. So this is, we have seen more calculation, more maths here. Okay, most of it is actually solving the maths. The basic is actually we need to get the real value, we need to get the imaginary value, and then we can compute the magnitude and phase. Okay, and this is what we call a frequency response. And what we have, we start the example with a difference equation. Okay, so this is where we need to know that one. In test 2 later, so these are the kind of a question that you will have. So it can start with impulse response. It can start with a difference equation. Okay, and then you need to plot something. Okay, any questions before we end our class today? Okay, I take though. So okay, so see you guys back next week. So again, reminder. So please do the assignment. Assignment for this week is critical because if you don't finish your visual notes, so other group cannot do comments on your notes, because when you do the notes, other group will need to comment your notes next week. Okay, so make sure you submit the visual notes on Jamboard. Okay, we have the link on Jamboard in e-learning. Okay, so bye everybody. So see you guys on next Tuesday.
Thank you, Doctor.
Doctor, about the assignment,